he moved to Brazil and he's there now at the Instituto de Física Teórica of the Universidad Estatal Paulista, and we just work on a variety of topics, including string theory, string cosmology, gravitational wave data analysis and modeling, and effective string theory of gravity, and really giving lectures about gravitational waves changing years a bit from what we have been hearing until now.
Thank you. So, okay, sorry for. Can we have more light here because I'm not using slides? So, or does it bother for reading the? It's better. Okay, okay. Forget it. Forget. Okay. Okay. So, good afternoon. By the way, sorry, this was just to try the green board. It's my first time with this huge green board. So let me type my email if you need to contact me for anything related to the course. So it's easy. It's my name and then the institution. It's possible to read, you know, Ricardo Sturani, unesp.br. So what I want to tell you in this course, in these 4 lectures, is to introduce you to the wonders of gravitational waves. I mean, now it's 8 years, 7 years, since more than 7 years since the announcements of the first direct detection of gravitational wave. So they are part of gravitational astronomy, if not on equal footing, but on a good standard with other probes of the cosmos. And so if you work in any related area, you better know something about gravitational wave, even if you don't work on gravitational wave. Actually, if you work already in gravitational wave, my course would be useless. I mean, but you need to know something because it's something that is huge, that is going on, is giving a lot of information. We are seeing a lot of things. So it's good for students to understand how we see things or we hear things, like people like to say, and what do we learn with that. Just to give you the tools, at least to read the paper, no, and to understand the physics content of the paper. So, but before I start, sorry, I arrived only yesterday night, and this morning was busy in a PhD defense, online, of course. And so I want to make a quick poll among all of you. So how many of you are from Buenos Aires? Just raise your hand. Ah, okay, not even half. So how many of you from the rest of Argentina? Okay. Then how many of you from, say, Chile? Oh, and then let's say, okay, Uruguay. Uruguay is next door. Oh, only 1, 2. Still. And then let's say Bolivia, Peru, Ecuador. Okay. Then Colombia and Venezuela. Well, Venezuela, I guess nobody. And then anybody who doesn't belong to these countries? Oh, a lot. Ah, sorry, Brazil. I forgot Brazil. Yes. So how many of you from Brazil? That's. And then what is the country I didn't mention? Dominican Republic. Oh, of course, Caribbean. Caribbean and Central America. Who is Caribbean, Central America? Yeah. So even after Caribbean, there is something missing. What did I miss? Mexico. Oh, yeah, Mexico. Yes, North America. Somebody from Mexico? Mexico. And now it's all? Did I get it, everybody? USA. Oh, you came all the way from the USA. Welcome. Okay, Central America. There was Central America and Caribbean. There was part. Okay, I got everybody, no? Now I need another poll. How many of you already work in say, cosmology? Just cosmology. Okay. Most of you are cosmologists, like CMB, perturbations, and so on. How many of you in astro? Say astro, not cosmology. Okay. How many of you in particle physics? I mean, you can have double affiliation. You can work in astro and cosmology. In particle, okay. Particle, I guess, theory. Experimental particle, also. Oh, also experimental. Very, very good, very good. Did I leave any field out? Somebody that doesn't belong to any of these 3 macro area? Yes, you belong to it? No. So these 3 macro area kind of exhaust your fits. Very well. No. So me, myself, I started the PhD in theoretical particle physics, but then I moved to gravitational wave well before the first detection. I was a visionary. And then my vision was rewarded 7 years ago with the detection. But you know, we were sure that, by the way, I have notes. I have these notes are on my Google Drive. You just need to have the link, and then these notes, there are 70 pages. There are much more than I will say in these lectures. But of course, as you know, I mean, what is written down in the notes should help you to have further think than what you hear in the lecture. So, okay. So we already know nobody was unsure the gravitational waves are there because of this. I guess you must have seen this, no? In some flavor. I will tell you in a second what is this. So this is, but I cannot write. What if I make? Can I use the board and the PDF? If I do this, and can I unmaximize this? Just draw. I can draw here? No, I cannot.
You can sketch the parabola in the
yes, but then I won't have the two at the same time. But anyway, let me go back here. So, you know, we have, so because of that curve, it tells you something very important about the binary system. So, you know, binary systems are very common, no? In our galaxy, for instance, because we cannot see much more. Individual system, we cannot see much outside our galaxy, of course, apart from gravitational waves. But in our galaxy, I mean, a good share of the stars are in binary system. We don't know exactly how many, but it's a good share. I mean, 20%, 30%. It's not 0.1%. It's a good share. So in particular, we see there are some compact objects, neutron stars, that are very common in our galaxy. So we see neutron stars. We see hundreds of neutrons, thousands of neutron stars. And some of them are in binary system. There are lots of them in binary system, but in particular, 18 of them are in binary system with another neutron star. So a neutron star could be in a binary system with a white dwarf, with another star, but 18 of them are in binary system with another neutron star. Why it's important? Because a neutron star is not emitting light like the sun, but is emitting light like in a lighthouse. So it's emitting a beam. So of course, the neutron star is emitting a beam pointing there, and this neutron star is emitting a beam pointing exactly to us. So this is the pulsar. So this is the neutron star that we can see. So the neutron stars that are emitting to us, the pulsar which are emitting in some other direction we don't see. And so this one goes around each other with some period. But then by observing them over time, we see that the orbit is shrinking. The p dot is of the order of 10 to the minus 12. Of course, time, the period is a time. You derive by time, you obtain a dimensionless number. And this number is very, very small. It's 10 to the minus 10. So if you plot the time of arrival, I mean, this orbit is slightly eccentric. So there is a specific point in the orbit which is easy to spot, the pericenter. So, and if you take note of the time of the pericenter, every time it passes by. So if the period is constant, so the time of the pericenter should be the period, time, the time of observation. But if the period is varying, then you can take a Taylor expansion. Of course, if it's varying, there's no point in stopping this Taylor expansion to first order. You can go on to infinite order. But already this number is so small that this is 10 to the minus 12, and the period is of order of hours. So if you observe for a matter of years, it's enough, the first order. And then basically what was plotted in that graph is exactly the parabola given by this t-square behavior of the time of the passage of the periastron, okay? So this is a parabola pointing downwards because p dot is negative. So this is an observation, and this observation is it's hard to explain unless you assume that there is emission of gravitational waves. Okay, so we'll demonstrate in this course how much you need. I need to change the size of this. Okay. Okay. You need to know something about the system. So in particular, we expect, I mean, of course, there could be many ways in which the system is losing energy and so is shrinking its orbit. But if we assume that it's shrinking orbit only with the gravitational wave, then there is a way to predict its shrinkage, its rate of change of the period. And let's do the following exercise then. So we have to know something about the dynamics, because it doesn't matter to know how much it's emitting if you don't know how much energy reservoir is in there. Okay, so the energy reservoir which is in there, what do you expect it to be? This object, where the gravitational wave that are going out, I mean, if they're going out and leaking energy out of the system, they might take these energies from something. Okay, where would they take it from? So the angular momentum is an expression of the orbital motion. No? Since there is orbital motion, there is angular momentum, but since there is orbital motion, there is also some binding energy. Okay, so I write here the binding energy of the system, which is. Are you happy with that? I wrote minus the kinetic energy. Okay, well, this is correct. It's not an approximation, no? Because it's an approximation because I assume circular orbits, which is not quite the case because the orbits are slightly elliptical. But I said it's kinetic energy plus potential energy, but potential energy is minus twice the kinetic energy. So at the end of the day, I'm left with the kinetic energy. Okay, and then you know that the velocity is related to radius and to the period of the orbit. I mean, these three quantities, they are not independent. Actually, one of the three fix all of the others for the circular orbit. You remember why? Because we have the Kepler's law, which is this. So this is the radius of the orbit. Okay, this is the radius of the orbit, and this is the velocity of the orbit. This is just Kepler's law for circular orbit. And then if you want to, so you see, if you fix the velocity, you fix the radius, and vice versa. But then you also fix the orbital period. Let's do it. Let's say that the velocity is 2 pi r over t square is equal to gm over r. So let's bring this r to the other side. Let's multiply by 2 pi. 2 pi, let's divide by t. Let's divide by t, okay? So up to now I just mixing with the Kepler's law. Just, this is something a kindergarten you should have learned this, no? You don't need a PhD to know this. You don't even need to work in astrophysics to know this. Okay, just I multiply, but then look at here. Here I obtain a v cube, 2 pi r over t, 2 pi over t squared, this is a v cube. And here I obtain a gm over omega, gm times omega. This is a fundamental relationship between the velocity of a bound system and the orbital frequency, okay? So the way I will use it extensively in my course is v equal to gm omega to 1/3. Okay, so radius fixes the velocity, velocity fixes the period. No? Omega is just the inverse of the period modulo on 2 pi. So this is the energy, and then we need the rate of decrease in the energy to have an estimate of this p dot. Well, that I cannot derive. That will be derived either tomorrow or on Wednesday or on Thursday. I mean, it takes some amount of physics to derive it, but let's try to guess it. Oh, I started with page, okay. I didn't start from the first page, so let's cancel. I want to eliminate the previous pages because, okay, it doesn't eliminate this. So let's go to the next page. So then we need to know how much energy is lost. Okay, so derivation of the energy is lost, I mean, it's highly non-trivial, and it will take one full lecture of this course. But let's try to guess it. So first of all, dimensional analysis. Energy as the units of mass. Okay, speed of light is always 1 for me. Okay, speed of light is always 1, so this is a unit of mass. This is energy divided by time as units. But there is one thing in general relativity. What is G Newton? G Newton is not a it's a constant, of course. I mean, this we do in non-modified gravity. But when you have G Newton, G Newton for me is just a converter. This object appears, for instance, in the Schwarzschild metric, Gm/r. C is, speed of light is always equal to 1 for me, so I always forget it. Gm/r is dimensionless, okay? This is like metric perturbation. So this tells me immediately that G Newton is a converter from mass to length, okay? It takes a mass and it spits out a length. So the unit of this is a pure number, okay? As a unit, when I put a square bracket, I mean, what is the unit? Okay. The unit of this is so mass and length are the same thing, provided that you put in the right power of G Newton. So time and length are, of course, the same thing because the speed of light is equal to 1. So you see, this should be a dimensionless number modulo some power of G. So I put the G here. This is G times mass, which is time or space. The derivative with respect to time, it has to go to a dimensionless number, okay? So it's a dimensionless number, so can it depend on the radius of the orbit? No, there are a few things it can depend on. No? It can depend on the mass of the binary system, the radius of the orbit, velocity, omegas, and it can depend on the mass ratio of the two objects. This is an object that I will use a lot, so let me define it here. It's the symmetric mass ratio. So when you have a binary system, you will say, oh, what is the mass ratio? Well, m1 over m2. But m1 over 2 is not symmetric. So people rather use this eta, m1 and 2 divided by m squared. This is dimensionless, and so it gives you a measure of how asymmetric is the system. So when it goes to 0, the system is very asymmetric. When it goes to 1/4, the system is completely symmetric, and it cannot exceed 1/4. And for instance, in terms of eta, you have the reduced mass that is written like the total mass times eta. That's trivial, okay? So it can depend on all of this, but this is dimensionless, so it cannot really depend on the mass, it cannot depend on radius alone, it cannot depend on omega alone, okay? It could depend on mass over radius, because we know that this is dimensionless, provided we put a G. Then it cannot depend on R alone. It can depend on V alone, yes, because V is dimensionless. It cannot depend on omega alone, but omega is the inverse of time. If I multiply by Gm, which is a length, it's okay. So it can depend on all of these quantities, but because of the Kepler's law we saw, all of these quantities are the same, modulo some powers. You remember, velocity was this guy to the 1/3, and velocity is this guy to the 1/2. So I don't need to put them. Okay, so we need a formula that can depend in whatever way on the symmetric mass ratio, and can depend on whatever way on V. So the right answer is, it happens to depend in some approximation that will depends polynomially. So this exponent, you cannot guess by dimensional analysis, no? Because these are two-dimensional numbers, so by dimensional analysis you cannot guess. But I want you to guess if this exponent must be positive or negative. So when eta goes down, the radiated emission should go down or up? Just think about it. If you don't want to speak loud, just think in your head. No, if the system is very asymmetric, no, I have the sun, a big, and the asteroid. The emission and gravitational wave should be high or low? Low, no, because the guy who is emitting is the guy who is running fast. So the sun is there sitting, and the asteroid is running fast, but it has little mass, and the mass is the gravitational charge. So this exponent should better be positive. Okay, and we'll see that this exponent is actually 1. I mean, you cannot guess from dimensional analysis. We'll derive tomorrow or the day after tomorrow. And then the power of velocity. So a system that is going slow or a system that is going at high velocity, who is supposed to emit more? So, no, I mean, this should be easy to guess, no? It should be the guy. This should be also a positive power. Which power? Well, that's I challenge any of you to guess it. You really have to do the computation, and after you do the computation, you get 10. This is highly, highly, highly non-trivial. That is v to the 10. Okay? And then here, of course, there is some numerical number, which you find, is it 32 over 5? But I mean, this, of course, is not very important. Sorry, the power is square, not 1, is square. Is 2, of course. We'll see why, of course. Okay, but again, we cannot guess that this is a 2, this is a 10. We can guess even less that this is a 32 over 5. But what we can guess, there must be some positive power of eta and some positive power of the velocity. Okay. Now, if we put together this formula, let me rewrite it. Let me write SC, just I don't care about. V to the 10. If I short circuit these two formulas, I can already guess, given the velocity or the initial radius or the initial period of the system, I can already guess what is the P dot of this system. Why? I mean, sorry, the other way. E over E dot. No. What did I do? Okay, as you can see. Apart from a factor, will be a P dot over P. Yes. Do you believe that? Yes, no? Because E is just a function. It's a monomial in the velocity, which is a monomial in omega, which is 1 over T, basically. No? When you do E dot over E, if you like, and you remember, this is a V square. Okay? So this is a V square, and this is a V to the 10. So basically, you remember V cube. You remember V cube was GM omega. So V cube is 1 over T. Or V is 1 over T to the 1 over 3. So when I take the logarithmic derivative, apart from a coefficient, this is the same thing. And so let's do E dot over E. Now, E dot over E, it has dimension, because of course the dimension of E goes away. So E dot leaves out one dimension of time, which apart from a G is a dimension of mass. So again, this can only give E dot over E. This will give me eta square, V to the 10, this numerical coefficient that I don't even bother to copy. And then I get eta, I get a 2 from the 1/2 eta m, sorry, this was GE dot. So I get GM V square. So overall, you see, there is 1 power of eta that goes away. So I get a numerical factor that I don't care about. I get V to the 10, V to the 8. Divided by eta. Eta, sorry. Eta is in the numerator, not in the denominator. Okay? And then I have the dimensionless number. Okay? So this is the E dot over E that tells me the P dot over P. So that tells me, if you like, this is the inverse of typical time it takes until coalescence. Or if you like, you take this ratio, you multiply it by the period, and you get what is the P dot that you expect to measure from the observation. So there is one important thing to think about here. P dot over P, it has dimension 1 over time. So in this formula, what is giving the dimension? Is GM, which is giving the dimension, okay? And so GM is not an astronomical time. So you can check, we'll derive in a second, that the time it takes to coalesce is of the order of 100 million years or billion years. So it's really a macroscopic, it's an astronomical time. But you make out an astronomical time out of a small time. GM is the mass of the object translated into length or into time. What is this translation? Let's open a new page. So what is the mass the mass of the sun is a fundamental unit for me. So GM is a fundamental, it's a derived length from the mass of the sun. So this is something that you need to know. It's hard to derive. This is 1.5 kilometer. So that's what I said. G is a converter from mass to length. Basically, it takes the mass of the sun and converts to 1.5 kilometers. Okay? And then if you want to convert to time, this will be 1.5 kilometer divided by 3 10 to the 5 kilometer per second. No, not second square, second. Okay? So let's do the math. This will give me 3 10 to the minus 6 seconds. 10 to the, am I doing right? 3 10 to the minus 5 seconds. Uh, 1.5, no, 3 is 2. No, wait, it's 5. Let's do things properly. So I multiply, this is 10 to the minus 5, and this is, no, it's 5 10 to the minus 6. Okay. Okay, so this is the mass of the sun in kilometers or in seconds. By the way, the mass of the sun is 10 to the 33, 2 times 10 to the 33 grams, but we'll never need this. I mean, this is just, you can Google it, and but we'll never need this. We'll never need the mass of the sun in grams. What you need is the mass of the sun is 1 in mass unit by definition, and then you need the conversion to kilometer and the conversion to second, and you just plug in the speed of light. The speed of light, I mean, you cannot possibly not remember. So look at this. You get a scale. The only dimensionful scale in your system is mass that sets the time to coalescence, and this is 10 to the minus 6 seconds. So how on earth is possible that with only one dimensionful scale of 10 to the minus 6 seconds, I build an astronomical time to coalescence? This is because v to the 8. Because v to the 8 is very, very small. So the velocity of this system is of the order of 10 to the minus 3, the speed of the light, which, if you think about it, is not too small. 10 to the minus 3, the speed of the light, okay, it's not relativistic, but in whatever ordinary experiment is large, no? It's 300 kilometers per second. But then if you have a 10 to the minus 3 here, you get a 10 to the 24 to increase those 10 to the 16, to the 10 to the minus 6 seconds. So if you take, for instance, this 10 to the minus 6 seconds and you multiply by 10 to, by a velocity 10 to the minus 3, so you get v to the 8 is equal to 10 to the minus 24. So gm over v to the 8 will give you something 10 to the 18 second. So what is this in years? So 1 year, this is also a good thing to remember. 1 year is pi 10 to the 7 second. Well, why pi? Of course, there's nothing fundamental. It just happens to be the same as the number of seconds with 3 digits. Okay, if you plug this in here, then you get roughly 10 to the 10 years. So 10 billion years. So you can get a really cosmologically, astrophysically big time out of GM, which is microsecond. Microsecond is the time light takes to cross a black hole of the mass of the sun. So this is the meaning of the conversion of mass to length. It converts a mass to the size of the black hole with that mass. And then because of this huge suppression, then you get an astrophysically large time. And then this is by interpreting, you see, the time to coalescence as p over p dot. But then you can take p dot over p and multiply by p. So p dot over p we are already estimated. You multiply by p and you get the p dot. So p dot over p, as we just estimated, was this v to the 8 divided by gm. Then you multiply by the period of the neutron star we observed, which is of the order of hours, few hours, it's 10 to the 4 second. And you see that when you put things together, you get a value of the number 10 to the minus 12. So the p dot, the variation of the period of the system, p dot is dimensionless because the derivative of period with respect to time. So it decreases, it's 10 to the minus 12. So this was an exquisite measure to make, but that's what this graph is plotting, is giving you. Escritorio, yes. This plot is showing this. It's showing the Taylor expansion of the time of arrival of a specific point of the orbit, that instead of being linear in space with respect to the previous one, it has this slow drift in time that gives you the parabola. The parabola is just the first order of the Taylor expansion, and it gives you this 10 to the minus 12. Okay, so today what I'm going to do is just doing some introduction with some order of magnitude computation to give you an idea of what we are talking about. So just to summarize, so we see lots of pulsars. We see thousands of pulsars in our galaxy. This pulse, they are rotating, and every time the pulse hits us, then we can measure. By this, we can measure with the exquisite accuracy the period of the pulsar. Some of them, a fraction of them are in binary system. Even a smaller fraction, we get thousands of pulsars, hundreds of them in binary system, and we get 18 of them in a binary system with another pulsar. That's exquisite. And actually, we're being so lucky that there is one binary system of pulsar in which there actually a binary system of pulsar, where a double pulsar. Both pulses are pointing to us. This is really a strike of luck, no? Because one thing, of course, this pulse is very narrowly being 10 degrees or so. So we see only a small fraction of all the pulsars with the beam pointing to us. But then there is one binary system for which the two beams of the two pulsars, they're both pointing to us. This is the double pulsar. Okay. And for this system, there are periods, orbital periods of order of hours, a bit more, up to days. Then we can, for few of them, we can measure this p dot, this variation of the period. And so we can check that this matches exactly the general relativity prediction. And just to frame this is all galactic, no? So we see this very funny object, the mass of the sun concentrated in 10 kilometers, basically. And then you can check the distance, of course, from the Kepler's formula, the distance would be of the order of million kilometers. So you get the mass of the sun concentrated in Buenos Aires and the mass of the sun concentrated in the size of Sao Paulo, and the two of them are orbiting around each other 1 million kilometers. And then we see this variation of the period due to the emission of gravitational wave. And you see, everything that I derive with basic physics, just Kepler's law, just some dimensional argument, and a little bit more. There is only one piece of dynamical information that we need, is this formula here, the quadruple formula. Where is that? Yes, this formula here is the thing that we are going to demonstrate, and we were missing. That is the only thing that I didn't demonstrate, but I will do tomorrow or the day after tomorrow. The only piece of information that you don't have to do all this derivation. Then let's put this in context. So okay, let's make it a bit bigger. So if this is the bulge of our galaxy, and then how many spiral arms have our galaxy? Oh, I don't remember. I just wrote 4, but I drew 4, but I'm not sure about it. So we are somewhere here. So and when we look in all direction, then we see these thousands of pulsars. By the way, nowadays pulsars should be very popular, because 2 weeks ago, you remember, there was this announcement by Nanograv. Nanograv basically monitor the signal from pulsar, from roughly 70 pulsar from different directions, and they saw that there was a correlated noise in the time of arrival of the pulses. And the correlation was ascribable to the passage of gravitational waves between the pulsar and us. And so in this way, they show that there was some gravitational wave passing by, and they managed the amplitude of these gravitational waves. We'll talk about it probably the last day. Okay, so we are here, and we see thousands of pulsars. Some of them are in binary systems, few of them are in binary system with another binary star, with another neutral star, and so they give this signal. And but our galaxy is just a dot in the universe if you look at cosmological scale. So what does it mean, cosmological scale? It means, for instance, if you look at the solar system, what is the scale of the solar system, or the distance the Earth to the Sun is of the order of 1.5 10 to the 8 kilometers. Okay, when we talk about astrophysical distances, that the most you can do with kilometers. You deal with kilometers only with the Earth-Sun distance of the size of the solar system, which are the order of tens of billions of kilometers. That stop it. You stop using kilometers. Then you start using parsec. And typically the size of our galaxy is of the order of tens of kiloparsec. How the parsec is defined, I guess most of you already know, but if this is the Sun and this is the Earth, you know the Earth goes around the Sun during the year, and this is 1.5 10 to the 8 kilometers. If there is a distant star that we are looking at, we'll observe a parallax of 1 second between summer and winter. And then if you want to translate this, if you measure the parallax and you know this distance, then you get the distance of the star will be 1.5 kilometers 10 to the 8, which is Earth-Sun distance, divided by 1 second. This is by definition a parsec. Okay, so but then if you want to translate this, we have to convert the second in radians and then to see what this actually means. And so we have 1.5 kilometers 10 to the 8, 1.5 10 to the 8 kilometers. So 1 second is 1/60 of a minute, which is 1/60 of a degree, which is pi over 180 of a radians. Then if you put everything together, this is, okay, let's see if I can do it right here on the blackboard. Anyway, I have my notes to correct me. So this is 1.5 times 3.6 10 to the 3 times 2 10 to the 2 divided by pi, and there is a 10 to the 8. If you put all things together, so this simplifies with this, 2 gives me 3, 2 and 1.5 gives me 3, so this should be 3 10 to the 13 kilometers. Did I get this right? 1 parsec is 3 10 to the 13 kilometers. Yes. So this is the conversion, and from now on we forget about kilometers. Okay. So we talk about kilometers only when we are talking about a binary system. A binary system can be kilometers, tens of kilometers, millions of kilometers away, but forget it. As soon as you go outside the size of a source of gravitational wave, you talk about the galaxy, intergalaxy distance, then it's parsec, the unit. Or even better, kiloparsec when you talk about the size of a galaxy, or megaparsec when you talk about the distance between the galaxy and its neighbor. So for instance, you know what is our neighbor? Our nearest neighbor galaxy is Andromeda, okay, barring the small galaxies. A galaxy which has a mass higher or comparable to ours is Andromeda galaxy, which is 0.7 megaparsec away. But this is not, of course, the average distance between galaxies, because this is the nearest galaxy. The average distance among galaxies is of the order of, let's have a new, of the order of 6 megaparsec. How do we get this number? Well, because we know what is the density, the average density of galaxies in the local universe, which is of the order of, I don't remember by heart. Let's read in the notes. In the notes, the average density is of the order of okay. Yes, 5 10 to the minus 3 per megaparsec cube. So the average density of galaxy is 5 10 to the minus 3. So this is the number of galaxy per megaparsec cube. Okay, you see, then when you take the square root or the third square root, not the third, the cubic root, then you get a typical distance of a bit less than 10 megaparsec. So there is our galaxy. In our galaxy, we are seeing these few objects. Then our galaxy is a size of tens of kiloparsec. Then when you go to the neighboring galaxy, you have to wait few megaparsec. Okay, less than 1 megaparsec in our case for the neighboring galaxy, but in general, the average distance is of order of few megaparsec. And then when you go to the scale of 100 megaparsec or more, then you get to the scale where the universe is really statistically homogeneous, then you start doing cosmology, okay? Because of course, up to 20, 30 megaparsec, in the galaxy you see one scatter here and there. When you go beyond 100 megaparsec, then you can start thinking of they are homogeneously distributed. And then when you go to the gigaparsec, then you are really in the realm of primordial cosmology. Then you really get into redshift, non-negligible redshift. Okay. So the other thing I want to say is that another good number to remember is the mass of our galaxy, which is the order of 10 to the 11, 10 to the, let's say 10 to the 12. It's a bit of an overestimate, but it's of the order of 10 to the 12 solar masses. This is the, sorry, yes, thank you. This is the mass of the Milky Way. And our understanding is that the universe was very homogeneous. No, you heard about it. I guess I wasn't here, but I guess you heard about it even in this course. So the universe was very homogeneous. Then here and there, the matter started to collapse just because of gravitational attraction, leaving a galaxy and a hole outside it. A galaxy and a hole outside it. Then, of course, the galaxy has a lot of non-trivial dynamics. They attract each other. They tend to be clustering around each other, then leaving voids and so on. But in first approximation, I won't be doing cosmological perturbation here. I'm just giving a rough, very, very rough picture. No? There are all the gas that collapse into galaxy, all the gas that collapse into our galaxy. But then if I take the mass of a galaxy and the typical average distance to another one, then that should compare more or less with the average density of the universe. Let's see if this is true. So the average density of the universe, if I take it from the mass of the galaxy and the typical distance, or if I just multiply by this, by the number of galaxies, it's easier. It's of the order of 5, 10 to the minus 3. No, 10 to the minus 3, sorry. So 10 to the minus 3, I put it here, then it gives me 10 to the 9. And then here in the denominator, I get megaparsec cube. Okay, so the density of galaxy, the density of the average density of the universe that I can infer by replicating the typical distance of galaxy and the mass of the Milky Way, and then again, is roughly of the order 10 to the 10 solar masses per megaparsec cube. So this is a very, very rough, a very, very rough estimate of the density of the universe. Let's check if this makes any sense or not. What would you compare it with? This is the density of the universe as measured. Let's take, there is a galaxy here that has this mass. I divide by the distance cubed to the next galaxy, the average distance cubed to the next galaxy, and then I get the average density. So if you want to compare with some cosmological input, what would you compare it with? Sorry? Very good, thanks. The critical density. So I have okay, this is a Friedman formula. I guess I don't have to justify because otherwise, I assume you know it, you see? This is the density of the universe, and this is the Hubble scale. The Hubble, we measure it. So let's see what is the critical density that it gives. So what is the Hubble is, I mean, you know there is a discrepancy. We don't know how much it is, but you can guess that for the precision I'm making this computation, the discrepancy of the Hubble doesn't really matter. So this is the Hubble as it is measured today, and it has these funny units, kilometer per second per megaparsec. So Hubble is the inverse of a length or inverse of a time. So why this has these funny units? Because historically it's been measured by recession velocity of galaxy. So it's velocity once you multiply by the distance of the galaxy you're observing. No? You should return a velocity once you multiply by the distance. So you see, there is a velocity in human units, kilometers per second, but the distance is astronomical units. Overall, this is the inverse of time, but it is funny units to take. I mean, the unit tells you exactly how it is measured. Okay, so we take this to the square. We multiply by 3 divided by 8 pi is 1/5. Let me simplify. 3 by 8 pi is 1/5. Okay, I guess you agree. And this is the raw computing with this other method. So let's do the math. So 70 squared gives me 5 10 to the 2, right? Or 5 10 to the 3. Divided by 5. Yes. And then I have kilometer. Kilometer square divided by second square divided by megaparsec square. Oh, wait. How can this ever be a density? A density is mass divided by volume, no? Where is the mass missing? There is the G Newton, no? That I forgot to put. You remember, G Newton is a converter between length to mass. So we'll basically convert a length scale to a mass scale. So we'll introduce a mass here, okay? So I take 1 kilometer, it should be 1.5 kilometer, but I take 1 kilometer and I convert it to, so I get 10 to the 3 was there. Then I get, you remember, G times 1 solar mass was 1.5 kilometer. Then it tells me that 1 kilometer divided by G is equal to 0.6 solar masses, okay? So here I get 0.6 solar masses because I took 1 kilometer divided by G. Then I'm left with 1 kilometer divided by megaparsec square. But then I have second square. So second square I multiply by the speed of light square to get the right unit. And speed of light square is 10 to the 11 kilometer per second square. So second square simplifies. 1 kilometer simplified with the kilometer, so I'm left with kilometer, megaparsec square. I just have to convert kilometer into megaparsec and I'm done. So this is 5 10 to the 2 solar masses. Then here I have a 1 over megaparsec square. Then here I have, I have a 10 to the 11 denominator, so 10 to the minus 9. I get megaparsec cube, and then I have 1 over kilometer. I have to get rid of the kilometer. Then I write 3 10 to the 13 kilometer divided by megaparsec. I derived it 2 slides ago. Yeah, I was right. It's 3 10 to the 13, yes. Then I simplify the kilometers here and here. I multiply all the things together, and then I get, I need some space, and then I get something horribly wrong. Sorry, I must have missed some powers. So this was 10 to the 3, was 10 to the 11. Ah, sorry, this was megaparsec. It's 10. One parsec was 10 to the 13 kilometer. 1 megaparsec is 10 to the 19. Okay? Yes. Ah, that's cool. Okay, for the next slide, thanks. So 3 times 5 that gives me 10, 10 to the 19. So overall, this gives me 10 to the 11 solar masses divided by megaparsec cube. Okay? Does it match with the previous computation? Where was it? Sorry. I lost the previous computation. Did somebody remember what I got earlier? Okay. Okay, it's off by more than a factor of 10. Okay, but it's not off by a factor of 2000. Okay, it's 10 to the 11, 10 to the. It's off by a factor of 10. But okay, this tells you that it's not too crazy to think that there was the gas that collapsed into the galaxies, that made the mass of the galaxies, and this matches the Hubble constant that gives you a dynamical measure of the density. But it's also probably not wrong that the mass of the galaxy came out, the density due to the mass of the galaxy came out smaller than the density that came out of H naught, because we know that the galaxies, they are not a major contribution to the mass of the universe. We have some extra contribution. We have the dark energy. So basically, as an order, since the mass of the galaxy makes, including dark matter, makes 20% of the mass of the universe, then this very rough computation is telling us that we are kind of getting a big picture more or less right. Okay, so let's go back to the big picture. So we are in our galaxy. We see few objects in our galaxy. The scale of a galaxy is the kiloparsec, this tens of kiloparsec. The distance, for instance, from us to the center of the galaxy is 8 kiloparsec. The size of the galaxy is tens of kiloparsec. Then we look at the neighboring galaxy, we go to the megaparsec. And then to have a huge number of galaxies, we have to go to the 100 megaparsec. Up to 100 megaparsec, we have 100,000 of galaxies. So that's already a remarkable number. And then when we go to the gigaparsec, we are really in the cosmological arena. And yes, and just to complete this part of the introduction, let me, by the way, there are questions so far before I slightly change topic? Okay, and then, yes, I don't have the notes here. The notes are here. So, yes, the estimate of the gravitational wave, yes. So, when we talk about gravitational wave, where do we expect to see gravitational wave from? So, if we, first of all, we have to think about what frequency are you looking at. Because the gravitational wave, I mean, in general relativity, there's no, I mean, in principle, everything is dynamical, no? I mean, in this moment, am I producing a gravitational field or a gravitational wave? I mean, gravity doesn't know about this distinction, no? There is my body, is sourcing a gravitational, very, very small gravitational field because I'm very thin, and my weight is very small, but my mass is under control. But the gravitational field doesn't really, I mean, I wave my hands, I produce whatever, you know? The gravitational, I have a Newtonian gravitational field that could be, in principle, be perceived a meters away from me, and could be possibly some gravitational wave produced by hand waving. And you know, they are all mixed in the gravitational perturbation. Okay? We'll see that this statement has to be qualified in many ways. First, because if gravity is quantized, now I'm not producing gravitational waves unless I manage to put together at least enough energy to make one quantum of gravity. But okay, this is a speculative point. Second, because there is a distinction in the gravitational field on what is a longitudinal mode and what is a radiative mode. I guess you've done already the Bardeen decomposition, no? SVT, okay. You know already about the SVT decomposition in cosmology. So I'm doing something simpler. I'm doing you probably call Bardeen decomposition? I call it SVT decomposition, scalar vector tensor decomposition. We do the scalar vector tensor decomposition in flat space-time, which is easier than the one in cosmology. But actually, even that, I find it too hard to write it on the blackboard. So I do something even simpler than that. I do the scalar vector tensor decomposition for the electromagnetic field, not for gravity. And then I let you ponder what you have to modify in going from the electromagnetic field to gravity. And this will tell us that there is a fundamental distinction between the gravitational field, which is mediating the Newtonian attraction, and the gravitational field, which is mediating radiation, which is taking radiation out of the source, radiation and angular momentum. Okay. How much time left I have? 10 minutes. Okay, very good. Yes, yes. In 10 minutes I can do this derivation. You see the point? I mean, intuition maybe works better with the electromagnetic field. Think about two charges, no? Okay, electromagnetic field, since we are born, I mean, we are very used to light, no? Nobody can doubt that light is an important phenomenon in our life. But something that is a bit more difficult to perceive, because every body we usually deal with is neutral, is Coulomb attraction. But since the first year of physics, you know there is Coulomb attraction. Charge attract, repel equal charges repel each other, opposite charges. I mean, this thing, the Coulomb attraction and the light, are two expressions of the same phenomenon, the electromagnetic field. So how can it be possible that the same field is responsible for two manifestations that phenomenologically are very, very different, no? One is attraction and repulsion, and the other is propagation of light, carrying energy, angular momentum, no? These two things are actually phenomenologically very different. They are unified by our description of electromagnetic field. But there is actually a theory way to distinguish the two, which is the following. Let's take the Maxwell law. Of course, I'm forgetting some constant, but this is not the point here. I don't want to put in the constant here. So is the gradient, the divergence of the electromagnetic tensor equal to the sources. Okay, then let's split it into components. So I get d0, f0, 0 plus di fi0 equal to j0. Okay, I'm splitting in space and time. This is of course 0 because f0, 0 is 0. Now let's split fi0. This is di a0 minus d0 ai, always equal to j0. Okay, so now let's apply the what I call SVT, scalar vector tensor decomposition, that in the electromagnetic case it's only scalar vector. So I want to say that the electromagnetic field is composed of a time component, which is a scalar for rotation, of course. And then the space part I decompose into a gradient and a transverse vector. Actually, the space, this is a 3 vector, and I decompose it into a longitudinal vector, which is the gradient of a scalar, and a transverse vector. So this decomposition is unique. Okay, for the time, I haven't decomposed anything. For the space, I'm just saying that the original field is equal to dia plus a bar I, with the condition that the divergence of a bar is equal to 0. Okay? So in this case, this relationship is unique and invertible, because for instance, if I take the divergence here, this gives me Laplacian, this gives me divergence which is 0, and I can solve immediately for the small a in terms of the original field. And then by subtraction, I get the a bar. Okay? A bar has 2 degrees of freedom because it has 3 components, but it has to be 1 constraint, so it's transverse, and this is clearly 1 degree of freedom because it's a scalar. Okay? So I'm just doing the Bardeen decomposition simplified for electromagnetic field and in Minkowski background. So just to give you basically the feeling of what is happening without the burden of all the difficult mathematics. So let's go on with this decomposition. I need another panel. So this will give, this was di is 0 minus d0 dia, which is equal to Laplacian of a0 plus a dot. Remember, this is d0 high is the minus the derivative with respect to time, because I'm using the metric minus plus plus plus. So d0 is equal to d in dt, or if you like, dx0, and d0 high is equal to d in dx0, which is minus d in dx0. And the time is the contravariant vector, is this one, is time. This is, sorry. I'm sure you like my style of handwriting, but okay. So this minus become a plus. So I get a0 plus a dot equal to j0, also known as rho. For friends, we can call it rho, the density of charges. Now let's go to the other equation, the space equation of Maxwell equation, d mu I, we specialize the free index to I, the vector part, so we get d0 f0 I plus dj fgi equal to, let's open now the f0. F0 will be d0 ai minus di a0, right? Plus dj ai minus di aj, right? And now let's plug in the SV decomposition. It's not SVT, it's not scalar vector tensor, it's scalar vector decomposition. So this will give me a AI double dot with a minus the IA double dot. Okay, I have decomposed this original AI into the longitudinal and the transverse part. So this is A0, it stays A0. So the A0 becomes minus the I. Oh, what is happening? A0 dot. And here I get plus Laplacian of AI bar. Plus Laplacian of the IA, because I decompose this A, and here I get minus, what is doing here? Minus the I of dj aj, the part with the bar goes to 0, and then I have dj dia, it gives me, oh no, it was correct, the I Laplacian of A. Okay? You see, when I decompose this A in A bar plus gradient of a small a, I get Laplacian of A bar, and then I get a Laplacian of the gradient of small a. When I decompose this with A bar, the J and J bar gives 0 by definition, and then I get the J small a, I get Laplacian of A. Then look at how nice this becomes. So how can I move things upwards? With this? Ah, cool. This is so, oops. And so look at this. Now let's collect the A bar I, becomes a nice box A bar I. And then I got this and this, I got it. Then look at all the other pieces have a gradient. So let's put a gradient in evidence. And then I have A double dot. I have minus A double dot. I have minus A 0. Sorry, the A0 was the other way. Was A0 high, not A0 low. Was contravariant, not covariant. And then I got all these two. And then these two simplifies and goes away. And this is equal to Ji. But let me do the SV decomposition also here. This is equal to Ji bar, which is the transverse part, plus the gradient of a scalar, the gradient of J. So clearly, this piece which is a gradient must match this which is a gradient. This piece which is transverse must match this which is transverse. So let's do it. So we get one equation. So wait. As you can see, this is the first time I use this black. I mean, it's wonderful, but you know, it's the first time. So let's go back to the previous to the time part. The time part gave me this equation. So let me copy downstairs so we have it. So we get Laplacian of A0 plus A dot equal to rho. This was the time component of the Maxwell equation. Then we get the space component of the Maxwell equation separates into longitudinal and transverse part. Let's take the longitudinal part is A, let's change the order of this. It's A0 plus A double dot, and I put the minus on the other side, is equal to minus J. Okay, I put the longitudinal part, and then I put the transverse part. The transverse part is box A bar A equal to J bar I. So I get 4 equations because this is a vector equation, but this actually has 2 components because I have 1 constraint. So these are 2 equations. This is 1 equation. This is 1 equation. So the transverse part of the vector field satisfies a box equation. So this is purely radiative. These are the two polarizations that are purely radiative. You understand? This has two components, not three, because of one constraint. And these two components, they satisfy a box equation. So this is really radiative, and this is propagating with the speed of light. So now look at this. This combination of the field, which by the way is gauge invariant. You can check this is gauge invariant because you know A mu goes into A mu prime, which is equal to A mu plus D mu lambda. So you see A0 takes a minus lambda dot, and A takes a plus lambda. A is the longitudinal part of AI. Clearly, AI, the longitudinal part of AI changed with plus lambda, and A0 changed with minus lambda dot. So this is gauge invariant, and it satisfies a Poisson equation. And you know what is the solution of the Poisson equation? Okay. Okay, this is the solution of that equation. You all agree? No? I take the Laplacian and I bring it there. Okay, this is only half a joke, no? This is not a complete joke, because we know you just plug in the green function of the Laplacian and you convolve with the source, and this is the solution. And actually, if you go to Fourier space, this is even less than a joke. This is actually what you do in Fourier space. Okay, so you see, this gauge invariant field is longitudinal in the sense that it's not radiative. It doesn't satisfy a radiation equation. It satisfies a Poisson equation. So this is the gauge invariant field that is responsible for the Coulomb attraction and repulsion. Okay. Physically, phenomenologically, this is very different from electromagnetic radiation. Why? Because of this, because it satisfies a Poisson equation. Then we have the real radiative equation for the two radiative polarization. And what about the extra equation? I mean, we have another equation for basically the derivative of this. So one field cannot satisfy two equations unless they are the same equation. Let's check that this equation is actually equivalent to this, because if it wasn't, then it would be impossible for a field to satisfy two different equations. Look at this. If I take the Laplacian of this equation, and if I take the time derivative of this, I take the time derivative of the first equation and I get Laplacian of A0 dot plus A double dot equal to rho dot. And if I take the divergence of the second equation, I get Laplacian of A0. Sorry, here was a dot missing. There was before. Of course, the equation must have two derivatives only. Plus A double dot equal to minus Laplacian of J. You see, I took the divergence of this and the time derivative of this. And then I get two equations which have exactly the same left-hand side, and the right-hand side is different. Unless, is this true? I mean, this must be true, otherwise our theory is screwed. You understand? If this wasn't true, I take this member minus this member gives me 0. This member minus this member gives me this. So unless this is true, my theory is inconsistent. But this is actually true, because you remember, this is Laplacian of this J scalar is equal to di of the original Ji. Is rho dot plus divergence of J equal to 0. This is the continuity equation. So this is true. So you see, in this way to decompose the degrees of freedom of the electromagnetic field, we realize that there are two radiative degrees of freedom. One combination of longitudinal degrees of freedom that appear twice. And what about the 4 degrees of freedom? Well, the 4 degrees of freedom is the pure gauge degrees of freedom. It doesn't satisfy an equation because it's completely free. It's gauge. It's not physical. So it doesn't have to satisfy an equation. Okay? So the same things happen in gravity, but it's just a little bit more complicated. In gravity, so in my notes you find the exact derivation of what happens in gravity. So in an electromagnetic field, you get one longitudinal, one gauge, and two radiative. In gravity, in general relativity, you have to redo the same construction as Julien did, but in Minkowski for gravitational wave, because we don't care. At the production of gravitational wave, the sources are kilometer size, so we don't care of curvature of cosmological expansion of the universe. You redo the same exercise, and highly non-trivially, you find again two radiative degrees of freedom, 4 gauge, and 4 longitudinal. Okay? So it's important you remember this, that physically, this is the distinction of degrees of freedom. So in electromagnetism, usually people don't have any problem to accept this, no? Because you have the Coulombic degree of freedom, charges repel and attract, and we all know that. Nobody is scandalized by that. We have light, and light has 2 polarization, and we have 1 gauge degrees of freedom, the gauge transformation. Basically, a very, very analog thing happens in gravity, in linearized gravity at least, because then you have 4 gauge degrees of freedom, because you have 4 transformation along the 4 coordinates. So you have 4 degrees of freedom of this h mu that you cannot constrain, that they are not fixed by dynamics, they are fixed by the gauge, so they are arbitrary. Then you have 4 longitudinal degrees of freedom. That basically means that on the top of the Newtonian potential, you have 3 more potential that they are relativistic generalization of the Newtonian potential. And then you have the 2 really radiative degrees of freedom that propagate with the speed of light. They are gravitational waves. So by the way, this took 50 years people to understand. I mean, general relativity is from 1915. Until the 60s, people didn't understand this. I mean, not everybody. Few people understood this, but the general community didn't understand this. In particular, Weil, in the 20s, he used to mock the people who didn't understand this by saying that, you know, gravity has 10 degrees of freedom, 2 propagate with the speed of light, the other propagate with the speed of thought, in the sense that you can give them any speed you like to think about. And this, Weil wrote it down in the 20s, but people actually became common knowledge and entered the textbook only 40 years later. I am already over time, so I can stop.
Yeah, it's time for Ricardo. Is there any good questions?
So don't burn all your question now because you have a discussion section. Okay, please. Yes, the coordinate transformation. No, you can transform the 4 coordinates. No, t, x, y, z, the way you like, and the physics will be unaffected. Of course, at the end of the day, you want to compare with experiments, no? And experiments will be more easily read in some coordinates than in others, no? Because when you do an experiment, you read some number at the end in your detector, and those numbers are related to some coordinate that you read. So you better be so that the coordinate you choose in your computation are aligned with the coordinate the experimentalist uses in the lab. But in principle, the theory allows any coordinate transformation. No? That's what you do in general relativity. When you write the G mu nu, you can say that I send it to another G mu nu prime, which is equal to the G, the previous one. Okay, if you took a general relativity course, you already know. If you didn't, then this is meaningless. But okay, that's usually the things. Now, when you explain something for the first time, either the person already knows it or it doesn't get it. But what can you do? Basically, this is the metric in the old coordinates. The metric in the new coordinates will be just a tensor times the metric in the old coordinates. And so these x's, the old and the new coordinates are 4 old coordinates, 4 new coordinates. And these are the 4 gauge degrees of freedom that you have. You can change the 4 coordinates the way you like. And this gives you those 4 gauge degrees of freedom, which are not physical. At the end of the day, for computational purposes, we like to work in a gauge where all polarizations, all time polarization, they said, I will derive it tomorrow. Tomorrow I will write this. I will write box h mu nu equal to 0. Then if you look at it blindly without any prior knowledge, then you say, okay, this guy is telling me that I have a tensor with 2 indices. In 4 dimensions, these are 10 components because this is symmetric. This is symmetric. And I have these 10 components, they are all waves, if you just look blindly at this equation. But that's why I wanted to introduce this today first. Look, be careful. The real physics is this, 4 gauge, 4 longitudinal, 2 radiative. Tomorrow, I will write in a specific gauge some equation that misleadingly write everything as radiative, but it's just an arbitrary effect of the gauge choice. This will be true with a lot of caveats. Okay, This will be true with a lot of caveats, whereas this decomposition is really right. Okay, so what we do when we, what we will do, actually you will do it because I will explain, then you will do the exercise. So what will happen is that we'll take, we'll take a source. This source will curve the space-time around it, and the nice thing of general relativity is so kind to us that basically the h mu outside the black hole is always smaller than 1. Okay, because it's 2 gm over r. Okay, so 2 gm over r by definition is always smaller than 1 outside the horizon. So what we will do, we'll solve, okay, when we solve the equation very far from the source and we just look at the wave, here h mu will be much, much smaller than 1. H will be 10 to the minus 20, so we don't care. But then when we go close by, and at some point we have to go close by, you know why? Because you remember that energy function that I wrote, the flux function that I wrote, energy v square, energy dot of v to the 10. That function has corrections. And those corrections, they come exactly by all the kind of interaction that happens here, very close by. So the energy is minus 1/2 me v square plus correction. Of course, here the coefficient is not 1, it's just correction v square, correction v4, and the E dot has also correction. So it's v to the 10 times some factor, and then 1 plus v square plus v cube plus all sorts of corrections. Remember the Kepler's law, v square is gm over r. Here, this is a correction which is of the order of gm over r, which is exactly given by this, by the fact that h mu is, yes, less than 1, but it's not negligible here, close by. So we can treat, so again, general relativity has been so kind to us that basically all the really strong nonlinearities are hidden beyond the horizon, so we don't care. Here there are nonlinearities, but they're kind of under control because h is always smaller than 1, or equivalently v is always smaller than 1. So it makes sense to make a perturbative expansion. That's what we'll do. We'll treat all sorts of general relativistic interaction that goes beyond the Newtonian interaction perturbatively here, because they are somehow under control. And when we are very, very far away in the wave regime, well, here you may think the gravitational wave behave much like electromagnetism, no? Because the decay is 1 over r, it's a massless particle. So here the analogy with electromagnetism works very well. Here the analogy with electromagnetism doesn't work because electromagnetism is not self-interacting. Here you will have a lot of self-interaction between gravitational modes. So here what we get inspired from is QCD rather than QED. So here, basically, all what we know with QCD translate to gravity. Of course, you have to change things. QCD has 1 index, gravity has 2 indices, you have more degrees of freedom, but in principle, the computation in QCD, they move it there. Here, all the phenomenology of electromagnetism kind of apply because the waves here, yes, gravity is self-interacting, but here are so small that the self-interaction are completely negligible. So it behaves like something which is not self-interacting. Well, again, this is wholly hidden by the black hole, basically. Gravity is really, it's in QCD in the sense that it's self-interactive, but unlike QCD, it's always weakly coupled. I mean, kind of. I mean, h mu can get close to 1, but never exceed 1. In QCD, no, it can really get strongly coupled, so you really have a reshuffling of degrees of freedom. In gravity, no. So basically, you cannot have a glue ball of gravitons, no. So you can always treat the interaction of, so let me put. So the gravitons don't make you can always treat them perturbatively, yes.
After this, there will be a discussion session at 4, so everyone keep your questions. Try to think questions for all the speakers that will be panel. And then let's have a coffee and reconvene at 4.